is to talk about using VPP and testing VPP. My presentation has two parts. One is focusing on CSIT, which I do the introduction to, and second part is actually about benchmarking VPP. I'm not a coder, I'm a user. Also, I'm learning how to read code, especially the good code. I'm going to talk about three topics. The first one is very short. It's about what continuous performance lab is about in FD.io. Then I'm going to look quickly and provide you an overview about the CSIT project, and there will be a deep dive into CSIT and into walk through the code on Thursday. And then we're going to look at some of the performance benchmarking numbers and maybe a demo if the screen works. When FD.io when FIDO got launched, one of the key properties of FD.io was to actually set up a continuous performance lab that is able to verify how well the VPP code and any adjacent plugins or code modules, how well are they programmed, how well are they engineered, and how well are they performing. And the idea originally was about basically building a continuous development and continuous integration lab as part of the foundation and the project to keep verifying functionality and performance. And ideally to pick up any issues with deterioration of quality in the software before the actual human-based patch reviews. It has been set up, and we have these slides are actually a copy from the presentation that Dave Ward gave back in January in the pre-launch event in FD.io. We actually have, this was at that time it was a wish list, and we have right now in operation a virtual testbeds and physical testbeds, and I will talk about them in a bit more detail. So that's Continuous Performance Lab. That's what the name that is being used, and I've heard it quoted earlier today. The project itself in FIDO is actually called CSIT, Continuous System Integration and Testing. We started, I think, in March. There's a few committers on the list and a few more people actually contributing code. I am a project lead. And for any detail, the landing page is listed at the bottom at wiki FD.io CSIT. What do we do? What the scope is? The scope is about testing functionality, whether it's conformant with the specs. The specs are RFCs. And how well performant the VPP actually works, the existing code and the new codes. Currently, we are mainly focusing on the unidimensional test, data plane, and some of the control plane, and you will see the current testing coverage. But we want to extend it across the programmability plane and also look at specific use cases, or the most popular use cases. All of the tests are executed and run in FD.io in the infrastructure run by Linux Foundation. So this is what is on the wiki, and this is what we stated and we executed against. Now, what the CSIT project is really about is, we have quite big aspirations. So we want to provide a close to real-time feedback loop to engineers, to coders, to you, that actually can give you a thumbs up or down or somewhere in the middle regarding the conformance to specifications. Specifications we want to follow, and we do follow, are, it's a networking software, so we're following RFCs. IETF RFCs. For the new things that do not exist, we clearly need specifications, and we want to base on drafts, but we need specifications. We also benchmark VPP against the performance and efficiency. So performance is, as you will see from the following slides, it's again a following set of network benchmarking standards like RFC 2544 or 2442. But it's measuring packets per second, is measuring bandwidth, and is also measuring the packet latency, packet delay, and packet delay variation. We also want to watch the efficiency of the compute platform usage. And that's where we define a metric referred to as CPP, cycles per packet, based on the telemetry we get from the computer, from the operating system, and also from the VPP itself. So we really would like to provide you with the feedback on the conformance, performance, and efficiency of platform use. So there are sort of three main dimensions. And we want to have it automated, and we want to give it into the hands of everyone. We're not there yet, but we're making progress, as you will see from the following slides. Why is this feedback so important? Well, we want to drive a good behavior and also a good practice, an engineering discipline into the code and into specifically the new code. Verify that the code works as the GOT or the original VPP designers intended. Looking at the design of our testbeds, we have defined two types of testbeds. The 3-node testbed, where we have a traffic generator pumping traffic through two devices under test. VPPs are devices under test, or the 2-node topology, where we only have a single device. We currently standardize on the 3-node topology. That's because we can, independently of the capabilities of traffic generator, we can test any encapsulation you can imagine. So we're not only defaulting to the baseline encaps like L2, IP4, IP6, but also the more exotic ones, VXLAN, Lisp, GRE, MPLS, and so on. So we have a test executor that drives the VPP API directly. And we also started to develop test cases to drive VPP through a Honeycomb agent using the RESTconf API. Now, those 3-node topologies are instantiated on the per job basis, and they're instantiated in both the virtual environments based on VMs, so VPP running in VMs, but also on the actual real bare metal hardware. So where are we today with the CSIT? We have a working system, and it is based on leveraging robot framework to define the test cases. If you're not familiar with a robot framework, it's a Python-based tool, and it basically provides you out-of-the-box libraries to define test resources and libraries. And defining a new test case is quite easy, is by either arranging and putting together existing keywords, or identifying and coding additional keywords and leveraging the rest. There will be a tutorial by one of the committers, Miro Miklus, on Thursday to actually walk you through the, for example, creation or coding of the new test case using the MaxSwap example that I think will be covered tomorrow or day after from the VPP data plane perspective. So we have an equivalent in CSIT. We have some bash scripts to basically handle the instantiating of the VPP instances based on the source code, as those VPP instances are instantiated on a per Gerrit commit basis. So today, when you commit a new patch in Gerrit into the VPP, one of the jobs that's running is called VPP CSIT viral verify, and this job will kick in and will execute a full suite of functional test cases on your patch. So we'll pick up your additional source code, it will compile VPP, it will bring up the 3-node testbed to life, and will basically test it. And it works. And then there are Python libraries that are basically used to define the robot keywords, and they are split across multiple types of programming the V4, V6, L2 functionality in VPP. And they're also responsible for automating topology creation and topology feedback and integration with a robot framework, as well as driving the packet verifier. We're using Scapy Python Scapy for functional tests. And we're using different generators, currently T-Rex for performance testing. There's a bit more on how the test cases are defined. This is just a placeholder. We started to write documentation. It is almost complete. So please go to this page and let us know whether it is good or bad, or whether it's whether you can actually follow, and based on the documentation, you're able not only to understand how the system works today, but also to create the new test cases. So what do we have running today? Well, you've seen this list quite an extensive list of VPP functionality shown, I think, 3 times today. So here is another one. However, this time, it's not what VPP supports, but what we're actually testing all the time. And in IP4, so we sort of split this against the data plane, control plane, encapsulations, and management plane. And the more, if the new categories arrive, we'll add categories. And then we basically coded all the baseline stuff. So the baseline routing for IPv4 with some security stuff, input access lists, and white lists and black lists are coded in and being tested. Same for IPv6 as of last week. And data plane, L2 cross connect, bridge domain, and then there are some other smaller aspects of control plane being covered too. We are currently in the phase of adding more and more encapsulations. So VXLAN over V4 is actually already supported. So here we go. VXLAN over V6, CSIT discovered some API bugs and some little other code glitches. So the coders, BBP project team, BBP dev, are fixing those. And every time we have those running robots discovering a bug in the VPP, there is a big hooray cheering from the VPP team. So hopefully we're going to have more of these. To really see the full list, and when I did deliver this similar talk in San Jose back in March, I actually had the output of this grep command on the slide. At that time, we had about 24 or 26 test cases coded. Now the output is, for functional tests, is over 75 or 80 test cases, and they are being added pretty much every day. We are releasing them on a weekly basis. In performance tests, we have proliferation of test cases, so I think we are well over 100. And we're in a stage where we need to group the test cases and give the developers a choice of which tests they would like to run. And at some point, we'll probably have to start policing it because we only have 3 physical testbeds. So functional tests run on virtual testbeds. We currently have them running on the viral infrastructure with 3 machines, each capable of 33 testbeds. So we have capacity of about 90 concurrent tests execution for the functional tests. For performance tests, we run on bare metal. We have only 9 machines currently hosted at LF. All Haswell 2699v3 processors, 2 sockets each. So we only have a capacity of 3 concurrent tests. And if you are in a room, and you are welcome to donate hardware, as we are in definitely a need of getting more computers and more NIC variations. If you're interested, please talk to me offline. Right now we have, as I said, there are Cisco UCSs with Intel 2699v3 Haswell processors, 2 sockets each. NICs include Intel X710, XL710, so Fordvilles, Niantic, of course, and I think 2 types of Ciscos, which we're currently not using. So in terms of types of tests we run, so we run the non-drop rate and partial drop rate searches. So we discover the actual forwarding performance every now and then. In fact, we're doing it twice a week in the automated fashion. We're running the long tests for performance trending, and we're running the short tests that can be run on the per commit basis. Different packet sizes, single core, multi-core, range of VPP configurations, as you can see from here. This is a subset of what we're testing from the functionality perspective, but we keep adding it in, and the range of NICs. All code developed in CSIT is modular. So currently for performance, we have drivers for T-Rex, which is a Cisco-developed open-sourced software-based packet generator. We have Ixia drivers in a pipeline, and we're looking for volunteers to code other traffic generators, Mungian and so on. It is, again, all our work is tracked on Jira. There should be a link at the end, but if you just go to jira.fd.io, you'll pick up CSIT project, you will see where exactly we are. The way that we are releasing the code is on a weekly basis, so there is a weekly release. And again, if you go to Jira, you go into releases, you will see what has been released and when. What are our main goals? State tomorrow, well, tomorrow is 16th of June. So provide as extensive VPP code coverage as possible. So we will be releasing basically a set of, basically a concatenation of all the CSIT weekly releases as part of the VPP release date. And we will also have a separate branch released at the time when VPP ships, so mid-June, so that everybody knows what is being tested and how. Everything we do is automated. So all tests are run by the Garrett Jenkins machinery hosted by LF. What will make CSIT project successful? Well, we need help. As you will see from our Jira Kanban swim lanes, we have a lot of work still on the to-do list. And we encourage everybody, and definitely every VPP coder, to contribute and help us cover their functionality from both functional perspective and performance test perspective. And we welcome everyone. So we run our calls on Wednesdays, and you can follow it on IRC or just join the call. So that was my CSIT thing. I have another 12 minutes to talk about VPP performance benchmarking. So that's a bit of the eye chart, and the projector resolution, I guess, doesn't help, or maybe it does. We have released, together with Dave Ward, a blog, and there is a bigger helping of the internet, please. And there is a bit of the text there that I wrote based on really derived from the Patterson and Hennessy book, an excellent book, Hardware and Software Interface, on how to measure work, and human work, computer work. So it goes through the evaluation of formulas of seconds per packet and instructions per packet, clock cycles per instruction, and so on. It comes down to really to try to normalize it across multiple microarchitectures and multiple platforms. It comes down to cycles per packet per core frequency. So we're basically trying to normalize and standardize around the cycles per packet as a metric, at least to compare between different platforms and different hardware platforms, different software platforms. And that's the metric that we're also implementing in CSIT 2. And based on the OS hardware, in this case Intel hardware, and also VPP telemetry. Daniel has already covered a difference between the network workloads versus compute workloads. When I started to work with VPP 2 years ago, actually at a similar time that Damian, although I was from the user perspective, the first thing I discovered is that, well, the way that the VPP or any packet processing application works, or should work, is quite different than the compute application, because it's all about network I/O, packet network I/O, and the budget per packet is nothing. It's as you can see here, on 10 gig, it's 67 nanoseconds per frame, whereas accessing memory on Haswell is about 70 nanoseconds. So you need to pay a great level of attention to how the software is actually using, how cache optimized it is, and basically count the clock cycles, which is not always the case for compute workloads. So when we actually run VPP, we measure the external behavior. So we treat VPP as a black box. Again, repeating myself, against the functional specs and reference performance and reference efficiency. But we also want to get a good understanding of what costs the clock cycles. And that's where the telemetry comes in. So these two slides are actually stolen from some previous dev boots we run. One is to look at VPP, CPP telemetry, and hopefully we'll have time I can show you the output of the show run, and that shows the breakdown of cycles per graph node. And then, of course, we want to test the use cases so that people, the engineers, but also people responsible for capacity planning, can understand and associate a cost, in this case, a cycles per packet cost, on a per feature or per use case basis. And here are some references of the standards that we follow in CSIT and also in the benchmarking work that I show in a moment. So IETF specs 2544 and 1242. We're working closely with OpenNV VSPerf group with Al Morton and Mariam and other members of the team. And we also deliver some presentations on the OpenNV Summit regarding the work. So I know you've seen those slides before, so this is just a recap. This testing has been done quite a while back. It was September 2015, where we tested with eAntec, OVS DPDK, and VPP code before VPP code got open sourced. These were the results at the time, and the configurations of those setups are available, and they do show slower performance for both OVS DPDK and VPP because they're running on a single CPU core. And both the control threads and the PMD DPDK threads run on the same core. At Cisco, we have two machines that at least I do all the reference benchmarking. These are the machines. Although the current configuration is slightly different, as I will show you in a moment. But there is a 2-socket machine, and the slides that follow show the statistics for this guy with 12 10-gig ports. And there's a 4-socket machine that was in the past equipped with 18 40 gigs, but I had to give up some of the Ixia ports, so I don't have that anymore. And that's how the guys actually look like in real, messy lab. It's an ocean away from here in San Jose. That's how far my poetry goes. And the 4-socket machine is looking like that. So, and I'm going to log in or try to log into one of them, internet permitting, to show you some of the sample outputs from both the generator and from the tester. So, if we look at this 12 ports setup, this is the 12 10-gig ports. We did tests versus OVS DPDK, and for AMIX bandwidth with VPP going on this chart up to 2 million routes. VPP performance did not change. One of the main reasons was the amortization for the vector of packets, whereas the OVS DPDK performance dropped down due to mainly the size of the EMC cache. For V6, slightly different chart. At the time of the testing, we did not manage to get V6 running with OVS DPDK, so we're only showing the numbers with VPP again at the rate. Now looking at the 18 ports setup with 4 sockets, we were able to get close to 300 million PPS. And the restriction there wasn't really the capacity we had on the sockets, but the PCI bandwidth and also the NIC performance. So the limiting factor here is not really a VPP software or the sockets, but it's really a network I/O. And then we added some security, and the performance didn't change. And what I wanted to show you here is looking under the hood on how much the features costs. And I don't know how readable this thing is, but basically we can tell VPP provides us with a telemetry on a per node basis on how many clocks per packet is actually being utilized. So here you can see 43 clocks per the IPCOP whitelist. And it's also showing that the VPP vector size is about 23 to 27. And the marketing sort of analogy made here is that this is, versus max of 255. This is like driving a 1,000 brake horsepower car at 10% capacity. So there is a capacity there to add more features. And we have quite a good telemetry, and that's actually one of the cool things with doing this in the open source. When I had to ask for features when at Cisco, I had to beg, borrow, and ask for favors. Some of you here. In FD.io, we just said that it would be cool to actually have the telemetry and like show run API. And then somebody shows up. I think it was Chris from somewhere, and says actually he's happy to code it, and we got it within 2 or 3 days. So we will be using this API to actually provide the feedback as just the automated generated report for every performance test going forward. So you will basically know how well your feature works and how many cycles it takes on the machines that we have in the lab. One other thing about the other test I ran where I forgot to switch off the tester, and it's been running for a while. It was quite a few days. It forwarded 18 times 7.7 trillion packets, and then I looked actually what the measurements were reported by Ixia, and it was reporting a packet delay, and somebody was asking me about, so what's the soak test you have in terms of packet delay latency, packet delay, and what's the minimum and maximum, and that's what it was. With the outliers, the worst packet was 3.5 milliseconds, but the average packet delay was at the level of 23 microseconds across the soak test, so not bad. And going forward, as I said, we are integrating packet delay and packet delay variation, and we are working to code, hopefully, on a per packet measurements, so that we always know each packet in terms of latency, and could graph a histogram for you. So this is a blog that we published over 2 months ago. There are some additional data there, and one of the comparisons that I wanted to draw your attention to is comparing a 4-socket server and CRS. And in fact, comparing a 4-socket server versus CRS. So, as I said, we were able to equip a server which is not network I/O optimized at all. This is off-the-shelf Cisco Enterprise compute load optimized platform. With only on 4 sockets, we had only 9 PCI times 8 slots, or actually 6 times 8 and 3 times 16. And we could still get not line rate, but not far from 18 times 40 gig. So imagine where somebody produces a computer that is actually network I/O optimized, where we could get 40 lanes per Haswell socket, and in Skylake it's supposed to, I don't know, double maybe. How much network I/O we get? Assuming we have an efficient software running on the socket, I think we can easily take even the bigger CRS. But I don't know. You tell me. Okay. So, any questions?
Just one question about performance in the figures that you presented. That when we increase the number of max or number of FIPS,
yep,
we got quite constant throughput of VPP. And my question is, how far it can go? Of course, it cannot be infinite. So what's the limit? Do we have any idea at what point we begin to
Yes,
increase?
we do. Yes, we do. So who knows from coding apart from Damian?
But we don't know yet.
So right? Remember the 70 nanoseconds to access memory? Mm-hmm. This is, once you're out of the cache, like you're out of LLC, you need to check memory. The more memory checks you do, mm-hmm, the performance starts degrading. So it's really the capacity of the cache and whether you can fit a table into the cache.
Okay, thanks.
So far, right now, I think the stuff I'm running here is 2 million IPv4. We tested 8 million IPv4, and there was no performance impact based on the configuration we have. Mm-hmm. With IPv6, we can see the impact.
Okay.
When you go to the 2 million and 8 million, you will see the impact. But then the question is, of applying the course. So let me see if I can do the hello world. So this is the working machine. It's forwarding packets. You probably can't see what it does, but I can't see either. But luckily, my laptop has a better resolution than this. So after the session, I'm around. I have a system running, so I can introduce you to it. It's currently running 14 million TPS on each of the ports. It's 12 40 gigs. These are Fordvilles, XL 710s, and I have 6 of them. If I go to this guy, and I show you the FIP, it's 2 million roots, IPv4. You can see I'm running 24 threads. They are distributed across both sockets. So I placed the threads got placed locally to the NICs. And what else am I supposed to show? Okay. So, okay, I had some misses. So this is the telemetry that I was talking about. We're picking up one thread, a worker thread, with ID 0 running on core 1. And you can see that we're not really running anything fancy here. It's really from the busy counters here, a number of calls. You can work out how many packets we are processing. And so we're really doing IP4 lookup. But the interesting thing here is number of cycles per function. So the code is built in a modular fashion as a graph of nodes. I will see if I can set up the ACL or a more complex test scenario where we can actually see the cost of applying ACLs in terms of cycles per packet. So that way you can judge on how efficient your code is, but also the cost on a per feature basis, and also how often they are hit. So as we were toying with Dave Ward, it's an excellent tool for not only engineers but also for bean counters, right? For guys who are looking at techno-economics, because they can actually tell you, or from the telemetry available, they can say on what is the cost of processing the packets, how many packets can you process with a feature, how many customers or services you can deliver using such a platform. So I actually love that. And another cool thing I found out is that the way that this is calculated is using a TSC clock, and this clock frequency is always the same. Now, I wanted to show you something else, but looks like the something else, my machine gave up a bit. So PerfTop doesn't work anymore, but you can see that we're using 24 cores, so we are fully utilized. We're using DPDK PMD mode. And unfortunately, we were playing a bit with Intel telemetry stuff, low level. We programmed some registers, so sudo PerfTop doesn't work anymore. But hopefully I can recover it later in the week, and we can also show you what is the, in fact, even from, I think, this screen, we can see what's the split on the busy nodes. So one of the things that we're always looking to optimize is not only processing the packet, but getting the packet over the NIC and to the NIC. It costs a lot. And I could have showed you using sudo PerfTop on which driver it is exactly, but you can work out that the DPDK costs here are high. So we would like to work with the DPDK folks to reduce them as much as possible. And I think this really concludes my talk. Are there any questions? Okay, thank you.